So we left off at 3.6, talking about goals for having a sketch of a rational function. And these are the goals that we need. And in particular, I talked about how to find the vertical asymptotes. This is the zeros of your denominator, slash roots of denominator. And the horizontal asymptote, there's three criterias. It depends on the degree of the numerator polynomial and the denominator of the polynomial. If they're equal, we're going to actually get the ratios of the leading coefficient over here. They're equal. We're going to get the ratios of 1 over 2. If the numerator is degree larger than the denominator, then that means we have no vertical asymptote, because afterwards we're just going to divide it out and we're going to get a polynomial function rather than a rational function. If our degree on the numerator is smaller than the denominator is going to be ideally bigger than your numerator, so it's going to overtake it. And that means that the asymptote will be 0, y equals 0. So those are the three conditions of our horizontal asymptotes. Depends on those three. Depends on degree of numerator versus degree denominator. Now, end behaviors. Well, with the end behaviors, we're actually looking at the horizontal asymptotes for end behaviors. That's how we can kind of tell what's going to happen at the very end. Now, we do need to identify the behaviors at our vertical asymptotes as well, but for end behavior, it's simply just going to be our horizontal asymptotes. Horizontal asymptote behavior. If there is no horizontal asymptote, then we'll talk about how do we identify the end behavior in particular. So now I want to actually go with a polynomial or a rational function. So let's take the example. Let's see. Let's take the example. X squared minus 4 over 2x squared minus or plus 2x. Let's call this P or R of x. Let's take this to be my rational function. I want to sketch this. So the first thing I gotta figure out is how to sketch this, and I need these four pieces first. X-intercept, y-intercept, vertical asymptote, horizontal asymptote. Now, at the end of the day, to do any of these four, it is almost always beneficial to factor first. So I would recommend factor first. If you factor r of x, you're going to have, this is the same thing as getting x plus 2, x minus 2, because it's a difference of squares. And on your denominator, I can actually factor this by GCF. If I factor out a 2x, I am left with x plus 1. Boom. So now I have my function in its general form and in its factored form. This can help me out find a few things. So let's discuss about how to find x-intercepts. Well, x-intercepts, if we remember, to find the x-intercepts, we got to solve for our equation equal to 0. Remember, x-intercepts are your polynomial of whatever input equals 0. So our y value is 0 at the end of the day. Now, with the rational functions, it's actually nicer, because when I set this equal to 0, the only time I ever have a fraction equal to 0 is if the numerator is 0. So for instance, 0 over 10, that's equal to 0. No other possible combination can get me 0. It has to be 0 as my numerator over any specific number besides 0 as my denominator. All right? If I divide by 0, that doesn't work. That doesn't exist. We don't talk about that. It's called indeterminate. However, if my numerator is 0, then I will have an x-intercept for a rational function. So to find x-intercept, find roots of numerator. All right, find your roots of your numerator. Well, in this case over here, if I try to find the roots of my numerator, well, set this equal to 0 right here. Then I have x is equal to -2 and +2. So I have the x-intercepts. X-intercepts. Great. I got one part of my graph, the x-intercepts. Now let's get the y-intercepts. Well, if the x-intercept requires me to set y equal to 0, the output value to equal 0, then the y-intercept requires me to plug in 0 for x. So if I plug in 0 for x, so plug x equal to 0, what's going to happen? Well, I get 0 plus 2 times 0 minus 2 divided by 2 times 0 over 0 plus 1. But I can't divide by 0. 2 times 0, that's going to give me 0 times whatever this is, will give me 0. So I'm going to be dividing by 0. So what does that mean? Because I can't divide by 0. Well, that means in this case, no y-intercept. You can get a value. It's just in our functions in particular that we're sketching, there is no y-intercept. And then moving forward, we have to look at the vertical and horizontal asymptotes. Well, if you remember a vertical asymptote, it's just the zeros of my denominator. So if I set this equal to 0, x is good. My vertical asymptote is located. It's the linear equation, x equals 0 and x equals, where is it at? What is it? -1. Now be very careful. These are points, and these are lines. You need to make that distinction. It can be confusing because when you do your sketching, you have x equals -2, x equals +2, x equals 0, x equals -1. They're all different. Be very careful. One has our sets of points, and the other one, or one of them are ordered pairs, and the other one are sets of points that create a line. So you have to be careful. Let me draw the 0 better. Now my horizontal asymptote. First, we check the degree of this polynomial. Let's go back to the original. It's much easier to look at it in general form for horizontal asymptote. Degree is 2. Degree is 2 for my numerator and denominator. That means I'm going to get the ratio of the numerator and denominator. And you know, this is the exact, or it's not the exact same, but boom. But it has the exact same horizontal asymptote as this problem over here. So the ratio of the leading coefficients, it's a 1 and a 2. So y equals 1/2. Great. Now, holes we have not discussed just yet. And in this problem in particular, we don't really have to worry about. So I know I listed it, or I listed it over here, but I will tell you, I will do a problem where we have a case where we have that, and we have to identify it. But right now, we do not have that at all. But now I have to look at the behaviors of my vertical asymptote. Because I have all this stuff right here, neat. Now I need to know my behavior of my vertical asymptote. So if I were to roughly sketch this for now, let's see. If I were to roughly sketch this function, I don't know how it behaves, but I know that my horizontal asymptote, let's draw my line, is 1/2. So it's around here. How do I believe I can make it dotted. Do not know for sure. But that's my horizontal asymptote. And then my vertical asymptote is 0. Oops. 0 and -1. -1's over here. And then we have x equals 0 as well. Oops. That's a bad one. These are the pieces my graph will never touch in particular. I need to know how it behaves on these asymptote. X equals 0, which is the y-axis. And this is x equals -1. So that means I got to understand the behavior to the left side of -1 and the right side of -1, then the left side of 0 and the right side of 0. They might not be the same. So I need to do a table in particular. So let's look at 0 first. Let's draw a table for 0. So behavior. VA. Vertical asymptotes. The behaviors at the vertical asymptotes. Well, in our case, let's do a table. And then first, let's check the table for as x approaches 0 from the right side. So that means I'm going to be plugging in a value bigger than 0. That's very close to 0. So say, so let's use x equals 0.01, maybe. 0.01. We're going to use that value. Well, if I were to do this value over there, then if I look over here, my function, let me just rewrite this piece right here because it's going to be very helpful for our functions. X plus 2, x minus 2. So r of x equals x plus 2, x minus 2, 2x times x plus 1. If I were to plug in 0.01 into my function, if I were to plug this guy into my function for the first guy right here, 0.1 plus 2. So this is a lot of calculations, and the main thing that we really need to know if it's positive or negative. That'll help us describe how my function will look to see if it goes to positive infinity or if it goes to negative infinity. So if I get a negative value, it goes to negative infinity. If I get a positive value, it'll go to positive infinity. I can understand its behavior that way. So if I plug in 0.1 to my first factor, 0.1 plus 2, I get a positive answer. So I get, and I encourage you guys to, be a bit more organized with your tables, which actually I will refine this table so we have something to actually model after. So give me 1 second. Let me see how in particular I can draw this table more clearly. So let me actually delete this bottom part and make it longer. Boom. All right. So if I plug in x 0.01, then the sign of it is going to be, for the first factor, I know that 0.1 plus 2, that's going to be a positive number at the end of the day. If I plug it into the second one, 0.1 minus 2, that's a negative number. And this is all divided by, now if I plug it into my denominator, 0.1 times this guy, well, that's also going to be a positive number. I don't care how small it is. I care if it's positive or negative. Because if it's going to go to negative infinity or positive infinity, my behavior. And then the last one, if I plug in 0.1, well, I get positive as well. Well, then this tells us that, hey, our function in particular, if I'm approaching from the right side, that means y approaches, a positive times a negative, that's going to be a negative answer, divided by a positive, it's still negative, divided by another positive, it's still negative. So y approaches negative infinity in this case, as x approaches 0 from the right. So as my function, remember, it can't touch these asymptotes, but as my function gets closer to 0, it's going to go all the way to negative infinity. So in particular, it's not going to be in this portion, but instead it's going to be in the negative portion, which is all the way down here. So my function will actually go like this. Get very close to this asymptote. And then of course it's going to follow along this behavior right here for this horizontal asymptote. Because with the end behavior horizontal asymptotes, it'll approach that. Okay, so I got one piece right there. Boom. Now I have to see what is the behavior on 0 from the left side. So now I got to do as x approaches 0 from the left side. So I'm going to take a value left of 0 that is very close to 0. Let's take x equals negative 0.1. All right, that's very close to 0. Well, if I plug in negative 0.1, into my function, let's check the sign of it. So the sign, if I plug into this first one, negative 0.1 plus 2, that's still positive because 2 is bigger than negative 0.1. So I have positive for my first sign. Good. What happens if I plug into the second one? Negative 0.1 minus 2, well, a negative minus another negative number, or subtracting a positive number, that's going to give me a negative value. All divided by, oops, it is all divided by. Now, if I plug it into this one right here, 2 times negative 0.1, that's going to give me a negative number, of course. And then the last one, negative 0.1 plus 1, that's going to give me a positive. So now if I calculate all this sign, what does the y value approach to? A positive times a negative is a negative. And if I divide that by a negative, that will become positive. And then if I multiply that by a positive, we get positive. So at the end of the day, my y value approaches positive infinity. So on the left side of 0, on my vertical asymptote, I should go to positive infinity. So this guy right here should be something along the lines of this. Oops. If I were to zoom in, this is my function still. I'm going to use purple because that's the color of our initial function that we chose. So if I were to draw it out, you might do something like that. All right. Hard to see that, but that's the idea. Now that's one vertical asymptote down. Now we have another vertical asymptote. We have to look as, and I'm going to erase this piece right here because we don't have enough space. So that's 1, which is great. Well, now we got to do the other vertical asymptote. So I'm going to do another table. As my other vertical asymptote was located at negative 1. So I have to look at as x approaches negative 1 from the right. Negative 1 from the right side. What happens? Make this table bigger, just slightly. Then I got to check the sign. Well, if I plug in negative 1 to my first piece, negative 1 plus 2, negative 1 plus 2, well, or actually, let me use a value. Let's use x equals negative 1 from the right. Let's do negative 1.01. That's very close to negative 1, but on the right side. If I were to plug that into my first one, plus 2, well, 2 is bigger, so that's going to be positive. My first sign is positive, good. And then my second sign, if I plug it into negative 2, well, that's going to be a negative number at the end of the day, so I get a negative sign, all divided by, fix that negative sign up. If I plug it into 2x, well, 2x times a negative number, that gives me a negative number. And the last one, x plus 1, so if I plug in negative 0.01 plus 1, I get that little leftover. It's going to be negative 0.01, which is still negative at the end of the day. So you have a positive times a negative divided by a negative divided by a negative. What does that give you? Positive divided by a negative, that is a negative, divided by a negative, that is a positive, times a negative, that is a negative number at the end of the day. So y approaches negative infinity. So in our graph, negative 1 from the right side is actually going to approach all the way to, if I zoom in, my function now becomes, and this is a weird behavior, it's going to go to negative infinity from the right side. Actually, so I apologize, but I just realized that this is actually to the left side because negative 1 is over here, negative 1.01 is on the left side. So I was actually doing the left side instead of the right side. So I apologize for that. But that's an easy fix up. So boom. So I did it on the left side. It goes to negative infinity, which means that on the left side over here, my function goes all the way down to my vertical asymptote. Boom. It's going to pass this, and then it's going to level out on the horizontal asymptote. Right there. And then you can kind of guess what the last piece is on the right side of negative 1. But let's just verify that. So as x approaches negative 1 from the right side. And now let me use a value on the right side. Let's say x equals negative 0.999. So that's on the right side, so I apologize for that earlier. If I did that, then the sign that I want, let's see. If I plug that into the first one, negative 0.999 plus 2, well, that's going to be a positive answer. The negative 0.9999 minus 2, well, that's a negative answer. So far, it looks exactly the same. All divided by negative 0.999 times 2, that's going to give me a negative number. And then the last one, negative 0.99 plus 1. 1 is bigger than that. Or I guess the distance from 0, 1 is larger, and 1 is going to overtake it. So we're going to have a positive answer at the end of the day for this final one. So that's the key difference. Everything was the same except for that final factor, which means that y approaches positive infinity because the sign changes. Positive times a negative divided by negative times a positive, they're all going to be positive at the end of the day. So the y value approaches positive infinity, which means on the right side of this, it's actually going to loop like this. This is what our function should kind of look like for the behaviors. Remember, the horizontal asymptotes, those are just the end behaviors. We're just going to look at the end behavior as it approaches that horizontal asymptote. So it checks out this way. Now, this is the idea. And then you also have your x-intercepts and your y-intercepts. We have no y-intercepts in our case, so it should not touch the y-axis, which if you notice, it does not, because our y-axis is also our vertical asymptotes in our case. The horizontal asymptote, the x-intercepts are -2 and +2. So, in particular, on our axis, this right here should be 2, 0, and this point right here should be -2, 0. So now we have fully sketched our graph. And we can verify this with Desmos, our calculator. So let's actually verify how this looks. We won't get the exact idea, but we have we won't get the exact image, but we will have a rough idea of how it looks, a rough sketch. So we had x squared minus 4 all divided by, so I don't make a mistake, all divided by 2x squared. As you can see, it's almost starting to look like it, plus 2. Is that it? Boom. So it doesn't really look like it as much until I zoom out. So let's see. Did I do something wrong? Boom, 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 boom. What was my function? 2x plus 2x. Sorry. Boom. There we go. Now it looks like that. So boom. It's not exactly, we didn't get it perfectly exact, but we have the rough idea. Our horizontal asymptote is actually right here. This guy never got close to our horizontal, but the other parts do. So that was the only part that might be finicky, but everything else has the exact same behavior as our rough sketch. Just to illustrate, this is our rough sketch, and this is the actual image itself. So we have a rough idea of how it looks. And this is what happens when you have more than one vertical asymptote. You can have this kind of behavior. So that checks out nicely. Great. Oops, sorry about that. Now, let's move on to some other types. So this is what happens when I have a rational function with even, or not with even degrees, with the degree of the numerator the same as the degree of the denominator. It checks out nicely. Sometimes your degrees won't be the same though. So what if instead I had something like this? So what if I had another example? Example 2. What if I had x minus 3 all over x squared minus 3x? Well, if we factor this out, we get r of x equals x minus 3 all over x times x minus 3 by GCF. And then, weirdly enough, there's one term on top, one term on your denominator, so I can cancel out. This cancels out to 1 over x. So, what happens when we're actually canceling out? Because in this case, it tells me my vertical asymptotes is going to be x equals 0. My horizontal asymptote, we check the degrees. The degree over here is 1, the degree over here is 2. 1 is smaller than 2, which means my horizontal asymptote is y equals 0. If your denominator is bigger for the degree, that means you'll go approach 0, which we can see over here as well. But somehow when I factor things out, normally I would have a vertical asymptote of x equals 3, but I canceled it out. So what does that mean? Well, in your graph, this is what you're going to be basing it off of. However, when you canceled out, canceling factors are holes in your sketch. They're open holes. They are open holes. That's where you're going to miss a single value. It's not going to be an asymptote in particular because it canceled out nicely. However, it will still be a part that we have to account for our domain. Just because we have a new function does not mean that 3 worked because we have to plug that back into our original function. So, in this case, we have a hole at x equals 3. Wherever x equals 3 for the y value, that's where my hole is located at. So it's very important you find out where the holes are located at. And then, now I need to figure out the other pieces, the x-intercept and y-intercept. Well, the x-intercept is just setting the numerator equal to 0. But I can't set the numerator here equal to 0 anymore. It's 1 over x, which means I don't have an x-intercept. Now, the y-intercept, and it makes sense because I have a horizontal asymptote of y equals 0. So I'm never going to touch that area. And same with the y-intercept. If I plug in x for 0 right here, I'm dividing by 0. So I don't have a y-intercept. So it's empty. There's no x-intercept, there's no y-intercept. So we're looking good so far. Now, can we look at the behaviors? So in particular, let's look at, we already have our horizontal asymptote. Let's look at the behavior as x approaches. And we only have one vertical asymptote, which is very nice. 0 from the right. And let me draw a table here real quick. This is a very big sketch, but oh well. And as x approaches 0 from the left. So let me choose a value that's right of 0, that's very close. X equals 0.11 or 0.1. Let's do that. And let's do x is equal to negative 0.01. And then we got to calculate the sign. Sine. If I were to plug in 0.01 to my function, and you can choose, do you want to plug it into the top or bottom? It doesn't really matter in our cases. You'll get the same results. So I'm going to plug it into my new function because that's much easier to deal with. If I plug it into my new function, 0.01, well, that means the sign is going to be, the numerator is going to be positive all over because 1 is positive. And I'm going to divide that by a positive number. So y approaches infinity. Now, if I do the sign for my denominator, or for x approaches 0 from the left side, negative 0.001, well, the sign here is going to be positive still. But then my denominator is going to be negative, which means y approaches negative infinity. So we have a rough idea of how to sketch this already. And if I want to try to sketch this, let's see, where's it at, the sketch? First, I draw my asymptotes, which in our case, our asymptotes are just the x-axis and the y-axis. If I could do this correctly. These are my asymptotes. I will never touch that area. And then it says here that I have no x and y intercept because those asymptotes, but I have a hole at x equals 3. But before I even do the hole, let's actually get our behaviors. 0 from the right side. From the right side, it says we're going to infinity. So this is x equals 0 from the right side. I'm going all the way up. And I can't touch this horizontal asymptote, so I have to level out. Now, 0 from the left side says that, from the left side, it says I'm going to negative infinity. So I'm going on this side over here, and I'm going to negative infinity. Well, I can't touch the horizontal asymptote, so I level out like that. It's going to be some behavior in this form. It's a bit more complicated than this behavior when you see the actual graph, but this is just a rough idea. Now, what other information? We have a hole at x equals 3. So 1, 2, 3. There is an open hole right here. Oops, right. Why it's not at 3? At x equals 3, there's an open hole. Wherever it touches my function. Boom. There's a hole right there. So now we have all of our important features for this function particularly. This is what happens. It's very easy to graph this if, you know, your degree of the numerator is smaller than your degree of the denominator, because the horizontal asymptote will be 0, so your function will just approach the x-axis. And then we can check what this looks like in our actual decimals. It might look a bit crazier than this, but this is just a rough idea at the end of the day. So the function that we had earlier was x minus 3, all divided by x minus 3, all divided by 3x minus 3. Boom. And then we have this rough idea, but let's see. This must be x squared, I apologize. X squared minus 3x. Boom. So this looks nearly exactly as our rough sketch over here. Boom. Now, the problem about the graphing calculator or anything, it will never show you where that hole is located at. But if I set this equal to f of x, it will never show you where the hole is because it's a single point. Your calculator has not infinite amount of points, but it has so many points that excluding a single point on the graph, you cannot see it. However, if I did f of 3, if I try to calculate that hole, it'll tell me it's undefined at 3. So right here, it's undefined. There's an open circle here. Even though you don't see it, look at, if I drag on decimals, it'll show me a closed circle. But the moment I hit 3, boom, an open circle. So you guys can't see. Let me zoom in real quick. So it's a more accurate illustration. So boom, it's a closed circle, but then the moment I hit 3, boom, I have an open circle. Most TI-84, 85 calculators will not show this behavior at all. So you have to be careful. You have to know that you're looking out for a hole in particular. Make sure that any factors you cancel out, you consider that part of your domain, or you exclude that in your domain, and that becomes a hole instead of an asymptote. So that is a rough sketch of our graph. Let me zoom this into 100 so I don't mess it up. Now, so we talked about what happens if they have the same degree, and then I showed you an example where the degree of the denominator is bigger than the degree of the numerator, which means my horizontal asymptote will be y equals 0. Now, let's go what happens if the degree on the numerator is bigger than the degree on the denominator. So example 3. What happens if I give you r of x equals x cubed minus 2x squared plus 3 all over x minus 2? So the first thing, let's see if we can factor it out first. R of x. Now, this guy, it's very similar to, well, let's see, boom, boom. This, if you were to actually do the rational root theorems or anything like that, or whatever, you would find that x equals -1 is part of the solution for the numerator, which means that this can be factored as x plus 1. So you would have to actually check by the rational root theorem. And then if you did long or synthetic division afterwards, you would get x squared minus 3x plus 3 all over x minus 2. And I'm going to save time by telling you that this, if you did the rational root theorem, it would not work. This is not factorable. And the reason why is because you have a complex root with imaginary components. So I'm just going to leave it as that for now. We don't really need to worry about imaginary components because they can't be seen on our graph. So now let's identify those features that we were looking for. So x-intercepts, y-intercepts, apologize. What else was there? Vertical asymptote, horizontal asymptote, and then I gotta check the behaviors, of course, and holes. So in here, nothing cancels out, so there is no holes. There's no holes at all anymore. Now, the x-intercept. Remember, to find the x-intercepts, I have to set the y value equal to 0, which means it's the 0 of my numerator, which means that I have x equals -1, and then whatever these values are, but they're complex, they're imaginary components, so I can't really see them on my graph regardless, so I don't have to put that in when I sketch the graph. The y-intercept, well, that's going to be whenever whatever I plug in 0 for my function. If I were to plug in 0 for my function, this is going to be 0 plus 1 times 0 squared minus 3, 0 plus 3 all over 0 minus 2. If I calculate this out, this is 1 times 3 all over -2, which is -3 halves. Boom. So my y-intercept is -3 halves. Oops. The y-intercept is located at 0, -3 halves. That's my y-intercept. My vertical asymptote is when my denominator is 0, or the roots. So that's going to be x equals +2. Now, my horizontal asymptote, the degree of the numerator, 3, is bigger than the degree of the denominator, which is 1. Which means, it's not -1, it looks like -1. Let me erase that. Boom, it's 1. That means that there is none. But this has an issue. Because there is no horizontal asymptote, I don't know how the end behaviors are going to play out. Because the end behaviors I showed you earlier, they approach your horizontal asymptote. But now I don't have a horizontal asymptote, so I don't know the end behavior of my function. So how do I find the end behavior? You do long division. You actually have to divide the numerator by your denominator. So there's multiple ways. You can do long division or you can do synthetic in this case. In this case, you can do synthetics, but I'm just going to show you with long division because it might not play out so nicely with some functions. Or it will play out nicely, but some functions will require you to do long division instead of synthetic. So let's just do long division real quick. We have the coefficients of our numerator is going to be 1, -2, 0, and 3. We need a placeholder for x cubed. Oh, sorry. This is synthetic. I'm doing synthetic by accident. Let me do long division. So the thing that is my dividend is x cubed minus 2x squared. I need a placeholder for the first power, which is plus 0x plus 3, all divided by my divisor, which is x minus 2. Now, to do long division, you look at your leading coefficient or leading terms and see what multiplies them together, or what multiplies my divisor to get to my dividend, which is x cubed. Another way to think about it is, what is x cubed divided by x? And then now I have to distribute this out. If I were to distribute this out, I get x, oops, this is x squared. I get x cubed minus 2x squared, and I'm subtracting, I use parentheses subtract. These cancel out, these, oops, this will also cancel out as well, so nicely. -2 minus -2x, that's just plus 2x, which they cancel out to 0. I drop down to 0x. Well, now I have 0x squared plus 0x. Well, that's going to be 0, so there's not going to be a term here. I drop down to 3 here. So I have x squared, I don't even have to write this out, x squared plus 3, or it should be a remainder, remember that, 3 over x minus 2. This is my new function once I divide it. So r of x equals x squared plus 3 over x minus 2 if I did long division. Well, if you notice now, this is a quadratic. This is a quadratic. Now, the whole purpose of this long division is to see the end behaviors. It will have the same end behavior as this function in here. Whatever the leading term is, if it's cubic, if it's quadratic, if it's to the 5th power, to the 6th, I'm going to look at the highest degree and then see the end behavior. If I have a leading coefficient of negative, then the end behavior will be negatives of the original end behavior. So in this case, it's an even degree. So that means the end behavior is upwards and upwards. Remember, x squared is a parabola. that opens upwards. So now I have all the or almost all the tools. I have one last thing to do is check out my behavior at my vertical asymptote as x approaches 2 from the right and as x approaches 2 from the left. So now I have to plug in some values. And I encourage you to use this function right here in factor form because it's just much easier to deal with, in my opinion. It's much, much easier. Now, let's plug in 2 from the right. So let's let x equals 2.001. What happens? And over here, I'm going to let x equals 2 from the left. That's going to be 1.999. Something like that. I don't know. All right. So if I were to plug this, let's check the signs. And let me write the original function or the factored function just so we have a reference to look at. So the factor, once I factor it out, I get x plus 1 times x squared minus 3x. This is our factored function. X minus 2. Okay. If I plug in 2.01, the first factor is positive. If I plug it into here, 2.01 squared, that's like 4.002 minus, so we actually might have to calculate this a bit. So if I calculate this a bit, actually, 2.001 squared minus 3 times 2.001 plus 3. Is this going to be positive or is it going to be negative? This is around 4 point, I don't know, 0001 minus 6.0001. I might have added an extra 0, so I apologize. Around there. Plus 3. Which one is it going to be, positive or negative? Well, this guy's positive. This guy's positive. This is the only negative. 4 plus 3 is 7, so it's automatically going to be bigger than negative 6. So we can say this is going to be positive for the other piece. And then for the final denominator, 2.001 subtracted by 2, that's also going to be positive. We're going to be left with 0.001. Okay? Now we got to check the sign of 2 from, oops, 2 from the left side, so 1.999. Well, 1.999 plus 1, that's going to be positive. And if I plug that into my function, squared minus 3 times 1.999 plus 3. Well, now if I calculate this out, let me actually just use this on a calculator real quick, just so I am sure. I want to give you guys the wrong thing. Squared minus 3 times 1.999. And all I'm checking if it's positive or negative, plus 3. So it actually turns out to be positive in our case. And this is actually a good time just to verify the other calculation that we did, which was 2.001. 2 from the right. Is it also going to be positive? Let's see if we did our math correctly. So it is positive. Yep. So they're both positive at the end of the day. All over. Well, actually, yeah, the numerators are all positive, and then 1.999 minus 2, that's the denominator, that's going to be a negative. So boom. So now we have our signs, which means now we can actually discuss the behaviors at those asymptotes, which, after I erase this, I made the box a bit too small. Boom, boom. This implies that y is going to approach, they're all positive, so y approach infinity. And right here is positive times a positive divided by a negative, so y approaches negative infinity. Boom. I have all of my important features to graph this polynomial. So let's get my sketch. Oh, what just happened? It's supposed to be gray. Boom. All right, ignore that. So now my asymptote, my vertical asymptote is at 2, x equals 2. So let's go ahead and do that. And I'm going to use orange because we have been using orange. What the heck? Erase that. Fortunately, I'm having some technical issues. Let me draw my function over here. Maybe that's the reason why it's too far to the right. There. So now I have to draw the function, the asymptote, and I can't do dotted line, so I apologize again. But x equals 2 is somewhere around here. Now, 2 from the, let's draw my horizontal asymptote. I don't have a horizontal asymptote, so that's going to be very strange. I do not have a horizontal asymptote. I do not have a hole. I have an x-intercept of -1. That's great. So x-intercept of -1. So -1's over here. That's all I really have. And I have, do I have a y-intercept? 0 and -3 half. 0 and -3 halves is around right here. Boom. That's my y-intercept. So I have these. What other information I have? Vertical asymptote, blah, blah, blah. Now I draw my end behavior. So the end behavior, it says they're both going to go upwards, which means at the very end, whatever my function does, it's going to go up on the left side and it's going to go up on the right side. Don't really know how to play out, but it's going to do that. And now we got to discuss the behaviors at my asymptote 2 from the right. It says that I'm going positive infinity. So this is actually a weird behavior because that means my function goes to positive infinity as I get closer to x from 2 to the right. But the problem is I have no horizontal asymptote, but it also tells me that my function goes, the end behavior should go up as well. But I already started up on the left side. It's going to positive infinity as I approach 2 from the right. So that means I have to somehow eventually turn. I don't know if well, I do know if I don't cross the x-axis because I don't have another x-intercept. So I don't cross the x-axis in this case. But I'm going to eventually come loop back around all the way to positive infinity on the right side. Now, if I do 2 from the left, it says I should go to negative infinity. So I should be down here. I should approach down here. Now, the issue is that I also have to touch these intercepts in particular. Oops. I also have to touch these intercepts. So to touch the intercepts, I start from all the way down here to negative infinity when I get closer to 2 from the left side, but then I have to touch these x-intercepts. So it might do something like this. Boom. Which is such a weird behavior that we have. And this is a very important thing that we're going to talk about because this actually has one last asymptote that we haven't talked about. But this is the behavior of our image. And if you notice, it looks kind of like a quadratic here. Why does it look like a quadratic? Well, when we did long division, we had x squared. That's the reason why it kind of looks like a quadratic. So let's graph this out just to see what we have. If I wanted to graph this out, I have my function was, what is our function? X cubed minus 2x, oops, use parentheses. X cubed minus 2x squared plus 3, all divided by x minus 2. So you see that it is similar to what we have drawn over here. We have this quadratic here, but then we have this function down here. Boom. So yeah, so we knew that it has to go to negative infinity on my vertical asymptote from the 2 from the left side. So when I go down, but then I have to somehow touch my y-intercept. So it eventually has to level out here to touch that y-intercept. But then it also has to touch the x-intercept here. Boom. And then it goes all the way up. I know this doesn't cross the x-axis because I didn't have an x-intercept on the positive side at all. On the right side of my vertical asymptote, I had no x-intercept. So it has to be up here somewhere. I don't know how high it is, but I do know it's up above the x-axis. So that's how you can get your rough sketch. And there's no holes in this problem right here. So that's nice. But this is what we call, this function in particular, well, we don't have an asymptote, another asymptote here, so I apologize. But if we had an image, let's say if this was squared, then we will have a new asymptote. And we'll discuss that right now. So the last thing we want to discuss, I'll discuss, is if degree on the numerator is 1 larger than denominator, there will be a slant / oblique. They call it oblique or slant asymptote. Once the oblique or slant asymptote is just an asymptote in a diagonal direction. That's it. Kind of looks like the slant right here. All right. It will have a slant / oblique asymptote. And how do you know that? When you do your long division, then the moment you do your long division, you're going to have a linear function. So in our case, we had a quadratic when we had our long division, but you're going to have a linear function. That linear function will be your asymptote. So you can do more readings on that, but that is the general idea of how you graph your rational functions. We studied how we can graph it if the degree were equal. That means the horizontal asymptote is just a ratio of my coefficients. The very beginning. What happens if, so degrees are equal, boom. What happens if the degree is bigger on the denominator, or smaller on the numerator than the denominator, which means I have a horizontal asymptote of 0 in this case, boom. I also talked about what happens if things cancel out. That means you have a hole in your problem. And then I also talked about what happens if your numerator is bigger than your denominator, which means we have to do long division because we don't have a horizontal asymptote, so we don't know the end behavior. Once you do your long division, that'll tell you how your graph end behavior will play out. If it's a quadratic, they'll both go up, unless it's negative, of course. If it's a cubic, one will go, the left side will go down, the right side will go up. So you do need to remember how to sketch your polynomial functions with rational functions. It does play a role. And that covers it for 3.6. I'll cover 3.7 tomorrow, and then that'll be the end of all the materials in chapters 3. Take care. Bye.